Hi everyone. So for this part of lecture, we want to look at the boundary condition of a wave, and specifically we look at the reflection and transmission. Okay, so it's boundary conditions. And we are looking at reflection and transmission. Okay, so here is what we are going to do today. Okay, so as an example of a wave, we're gonna look at a wave on a string. Okay, so you may say it's very special case. There are so many other type of waves, and we want to look at the electromagnetic waves. The point is that again, there are a lot of common things between waves, and whatever in terms of the magnitude, oscillation, and what happens at the boundary, that we're going to discuss today. For a string, the same mathematics, you will be surprised, the same mathematics works for electromagnetic waves when they are transferring through the boundaries. Okay, so in a way that what we are doing looks like mechanics, but and looks like a very simple special case, but it's going to be very general. It's going to even work for sound wave, and as far as I can tell, for most type of waves, it's going to work. Okay, so what do we mean by reflection and what do we mean by transmission? Okay, the idea is this: when a wave propagates, okay, in a medium that everything is constant, the same, it's just continuous propagation. As long as there's no energy dissipation, right? As long as there's no energy dissipation, the wave is gonna just go move forward. As soon as the wave sees a boundary condition, okay, and that means the medium is changing, then some interesting things can happen. Okay, every boundary condition, the way it works is that part of the wave is going to get reflected. Okay, as soon as there's a boundary, part of the wave is going to get reflected. What percentage of the wave, then that all depends on the wave and boundary condition. Okay, and part of the wave is going to get transmitted over to the next medium. Okay, and as an example of that, you can assume you are looking in a glass, right? If you look at the glass, part of the light is being transmitted and part of the light is actually being reflected. If you are sitting in a bright room and there's a window to the dark room, like if it's at night, you're sitting in your room and looking outside, you see a lot of reflection. Okay, so you see a lot of reflection, but you know there is also a lot of transmission. Okay, so the same thing happens in waves. And in fact, the example of the light that I just said, that's related. That is related to waves as well, because light is one type of electromagnetic waves. Okay, so now let's focus on what we want to do. The easiest way for you to assume a wave is just imagine you have a string, and now imagine you have one single pulse of a sine wave. Okay, so in what we're gonna do, we're gonna assume a continuous wave. Okay, but for purpose of demonstration and helping you to imagine what's gonna happen, just imagine one single pulse of a sine wave on a string that is moving this way with a velocity. I'm gonna call that v1. Okay, and let's say at this point, okay, what happens is that in a way nothing happens except that we connect this through a very light knot to a second string. Okay, and this second string is a different material and has a different mass. Okay, so as soon as we are moving from one string to the other string that has different mass, then this becomes a boundary condition. Okay, so for the sake of simplicity in the mathematics, let's assume that this boundary condition is happening at z equals 0. Okay, so what's going to happen is that this wave is going to move forward very smooth and nice. it's gonna see the boundary condition. Some part of the wave is gonna bounce back. Okay, so it's gonna come back like this. Okay, by the way, the shape could be exactly the same thing or opposite depending on, we will discuss, depending on the boundary condition. But part of the wave bounce backs, okay, and it's bounced back with the same velocity, okay, but it could be very well be different amplitude. Okay, if the reflection is not as strong, it's gonna come back with very tiny small amplitude. Okay, but velocity remains the same because you remember velocity was dependent on tension and mu, which is the mass density. Okay, so velocity is going to be the same because tension and mass are the same, but amplitude can change. And part of the wave is going to get transmitted to the other side. Okay, as soon as it's transmitted to this side, again, amplitude can be different depending on what percentage of the power is being transmitted. But as soon as it transferred here, it's going to move on with a constant speed. Here, I'm going to call the speed V2 because this is a different string, different mass, and that will affect the velocity. Okay, so if, by the way, tensions are the same, okay, but velocity can be different. Okay, so this is what I want you to first imagine before we start any mathematics. The wave is coming this way, sees this boundary condition, it's going to come back, same velocity, different amplitude, and part of the wave is going to move forward. Okay, the part that moves forward has more or less the same shape of this. Okay, the same shape is going to move forward, but different velocity. Okay. Again, now let's look at a few constants and variables that we will be using here. One of them is the tension. Okay, so tension on this side actually defines tension on the other side as well. Okay, because you have connected these two strings, the tension on both sides are going to be the same. So I'm going to see T here and T here with no subscripts to show that these are the same. Okay. So T is the same. The frequency or angular frequency omega of both waves are also the same. The frequency is not going to be dependent on the medium. Basically, the frequency is defined by the wave that is created. Okay, so if you think this is a string, you are holding one corner of it and moving it up and down to create a wave. The frequency is defined by you, right? The frequency defined by how fast you're moving your hand. Okay, it has nothing to do with the geometry and shape and mathematics of these strings. Okay, so you create the frequency, and the same frequency is going to get propagated here, and exactly the same frequency is going to get transmitted to the other side. Okay, so again, omega frequency, angular frequency remains the same as well. Okay, so what is different now? What is different? First of all, we chose two strings with two different mass, linear mass density. Okay, so I'm going to say here, this is mu1 and this is mu2. Okay, and since mu is different, mass is different, the velocity is going to be different as well. To remind you, velocity v is equal to the square root of t over mu. Okay, tension is the same, but mu is different. That makes v different. Okay, so this is the velocity. Let me write down what I have. This is T is the tension, omega is angular frequency, mu1 and mu2 are linear mass density, and v here is the velocity, transmission wave velocity. Okay, so now what we're going to do is that I want to set up equations can describe the wave on this side and set up the wave that is on this side as well. On one side, which I would mathematically call that z, negative z side, okay, z is smaller than 0. Here, technically we have, okay, let's put it this way. Mathematically, we have two waves. Okay, one wave is incident wave, the other one is reflected wave. Now, if you try to imagine we have continuous sine wave coming in, not just a single pulse. If it's continuous wave, it's very hard to track it. And then we will have continuous reflection as well. Okay, they all get mixed. Okay, so if we have continuous waves, incident and reflected wave, by eye it's very difficult to distinguish between them. Okay, but now here just imagine there's one single pulse. Now you can easily imagine this wave is moving forward and this wave is coming back. For the equations, I'm going to use a continuous wave because that's helpful and it makes things a lot easier. Okay, so I'm going to say we have an incident wave. I want to use the complex notation and use F tilde. Okay, and I'm going to use the substitute of subscript of I means incident wave. And this wave is a function of z and is a function of t. Okay, so it depends on the position, it depends on time. It's an equation for a wave. Okay, in complex form, so I'm going to use amplitude I, which includes the delta wave number as well. I'm going to multiply that by exponential of I times k1z. K1 is a wave number for the first string, okay, and minus omega 3. Again, omega is angular velocity, and it's the same for both sides. K is a wave number, and that's not the same for both sides, okay. So this is an equation for a continuous sinusoidal wave moving in the positive z direction, okay. The fact that here I'm using positive number k1, that means the wave is moving to the positive direction. Okay, so we have this one, and if you wanted to show that if it's going to the negative direction, by the way, you needed to use negative k1. Okay, so this is incident wave. And this is part of the wave equation for only places that z is smaller than 0. Okay, at 0 and positive 0, it's going to be different. Okay, so then this wave is moving to the positive I direction. We will have the reflection now. Okay, I'm going to call that FR. Again, it's going to be function of z and t. And equation for this, I'm going to say that the amplitude is AR. Amplitude is going to be definitely different from AI, unless the whole wave is coming back, okay? Reflection, you only get certain percentage of the wave power coming back. So AR is going to be usually in terms of the magnitude a small number, okay? So I'm going to say that AI e to the power of I times, now I need to be careful what numbers I'm putting in here, okay? So for wave number in the first string, it has to be K1, okay? It has to be K1, and the sign, as I said, defines the direction. Reflected wave is coming back, so I need to put negative times K1. And the value of K1 is defined by tension and mass density. Okay, so K1 is inversely proportional to V1. Okay, so K1Z, so this part, okay. How about the frequency? The frequency, as I said, is defined by the person who created the wave. Okay, so it's going to have the same frequency, okay, omega t, and it's going to be the reflected wave. Okay, now if you look at this, it's beautiful. These two are in a way very similar to each other. They have the same frequency, the same wave number in opposite direction. Okay, what changes is actually the amplitudes. Okay, and of course this is the complex amplitude. That includes the amplitude plus the wave constant. Okay, again, reflected wave in terms of what position we should use that to define the wave, it is for the negative side. So it is for the z smaller than 0. Okay. Now, let's look at the wave that is transmitted to the other side. Okay, so for that I want to use the equation similar f transmission, okay, f sub t is function of z and t, and for the amplitude I want to use at, and for the wave equation now we got to be careful. We have e to the power of I times for the wave number. Now we cannot use k1 because we are moving to the second part, which has the mass density of mu2, velocity of v2, so I'm going to use k2, okay. Negative or positive? It has to be positive because the transmitted wave is moving to the positive z direction, so it goes k2z. Frequency, same story, set by the person created the wave, omega t. So all these omegas are the same, and I'm gonna call this transmitted wave, and this is for z greater than 0. Okay, so we got this one as well. So we have the general equation for the waves, and one thing we need to do is that we want to specify the AI, AR, AT, or more exactly, we need to specify AR, reflection, and AT, transmission based on AI. Okay. I use K numbers here, so let's just clarify that K is inversely proportional to the V. Okay, so if you use ratio of V1 over V2, which is equal to lambda 1 over lambda 2, and that's going to be equal to K2 over K1. Okay, so there's a bit of intuition you can use to imagine what V should be. So see, V is proportional to, is the square root of T over mu, right? And then T is a tension. So if you have this string and try to hold it stronger so that tension increases, that way you are increasing the velocity, okay? But the mu, the mass density, is a denominator. That means if your string is light, V is gonna be big, and if your string is heavy, the speed of the wave is gonna be slow. And I'm pretty sure you have experienced that if you have a string or something or wire, if it's very heavy, if you want to create a wave, like by moving your hand, what happens is that you're gonna see the wave, okay? But if it's very light, okay, let's say a very, very thin string, you can't even see the wave because as you are moving it, the whole wave is gonna move, okay, super fast. So it's a bit of, just wanted to give you a bit of intuition how tension and mu work together to create a velocity, define the velocity of the wave, okay? So we have these wave equations set up here, okay? Now, I want to see what happens at the boundary, okay, or call it the joint, okay. So at the joint, what happens is that, by the way, this is happening at z equal to 0, okay. So one thing for sure is that we need to have continuity at this point, okay. These two strings are connected to each other, right? That means that the wave should be exactly defining the same amplitude at that point, okay? So for that, I would formulate it as f, okay, of at the position 0, negative, okay, that means a little smaller than z equals 0. At any time t, it should be equal to the wave at the position 0 plus, meaning a little at the positive sides, and t. These two needs to be the same, okay? So if I want to draw this boundary here, okay, so this is z equal to 0, at any point wherever the first string is coming at, okay, that's exactly the same point that the second string should pick up the wave. Okay, so the value at this point is the same. Okay, so this is the continuity. continuity condition, okay, that we needed for the wave. The other point is that the knot itself at z equals 0, it's a tiny small thing that has no mass, okay, so this is something super tiny, and the tension on this side has to be the same as tension on the other side. So in terms of the magnitude, we already said they are the same, right? But if in terms of the force and direction, if it has to be the same, that means this angle should be exactly equal to this angle. And that means the slope, the derivative of the wave with respect to z, has to be the same as well. Okay, so for that condition, I would say the derivative of f with respect to z at 0 negative should be equal to the derivative of f at z at 0 positive. Okay, so this condition is the continuity of a slope. Okay, so we should have continuous slope at 0. Okay, so we're gonna use these two conditions to relate the amplitudes of the reflected and transmission wave to the incident wave. Okay, so for that, let me move on to the next page. It's a little bit of mathematics. Okay, so I want to write what is the wave at z equals 0, because I want to use that for the continuity and also for the continuous slope condition. At f equals 0, we have two parts. If we are looking at the z equal wave coming from z smaller than 0, then we have incident and reflected wave. Okay, and because I'm writing this for z equal to 0, what's going to happen is that all the k components here that we talked about, okay, these z values are going to 0. So this vanishes, the same here and the same here. Okay, so getting rid of those parts, it looks a lot more simple. So at z equals 0, we have ai e to the negative I omega t, and then we have a reflected e to the power of negative I omega t as well. Okay, and then for the transmission side, if we go a tiny bit to the positive side, then we're gonna have a transmission e to the negative I omega t. Okay, so for the continuity equation, we should just make these two equal to each other at z equals 0 at any time. Okay, now if we look at this, all these time dependent exponentials are the same. They are exactly the same. So from the continuity equation, I would say we can set up the equation as a incident amplitude plus a r amplitude. Okay, so these two combined, coming from the top one, should be equal to the transmission amplitude. Okay, so this is one equation we could came up with. But remember, what we wanted to do is that we wanted to define find both AT and AR as function of AI. Okay, so we do this, and this is one equation so far. Okay, for the next equation, we should look at the continuity of a slope. Okay, and if we look at the continuity of a slope, we should take the derivative of this with respect to z, and that's going to bring a k number from the exponents back here. Okay, so if we repeat the same thing for the continuity of a slope, we're going to come up with this equation. Let's say continuity of the slope, and we're gonna come up with the equation of K1, okay, times AI minus K1 times AR. Okay, so here I put a negative sign because when we take the derivative with respect to K, if you remember, the AR, the reflected part, had a negative K number. Okay, so just showing it back here, the reflected side had negative, so if we take the derivative with respect to Z, a negative K1 comes down. Okay, so here we get K1 AI negative K1 AR, okay, and that has to be equal to K2 times A transmit. Okay, so we got this sign, these ones, and so two equation, two unknown, trivial, okay, even though they are complex, we can solve it in terms of the complex numbers. And if you solve that, you can come up with AR and AT being equal to, on this side, we get K1 minus K2 over K1 plus K2 AI, okay, and AT in terms of AI is going to be 2K1 over K1 plus K2 over AI. Okay, so we came up with these AR and AT, but remember these are in terms of the complex numbers. These are not the real amplitude, these are the amplitude in complex notation, which include the wave as well. Okay, so the same equation, if you want to write it in terms of V, velocity, and not K, only thing we need to do is that for each of them we should use K1 and K2 are inversely proportional to V1 and V2. Okay, so if we switch between V1 and V2 in the same, between 1 and 2 subscript and use V, it's going to do the job for us. So it's going to be AR is going to be equal to V2 minus V1 over V2 plus V1 times A incident, and A transmitted is going to be equal to 2 V2 over V2 plus V1 times A incident. Okay, so we came up with these complex amplitudes. Okay, the next step is expanding these complex amplitudes, okay, expanding these complex amplitudes in terms of the real amplitude and the wave constant, and from that we will come up with how the wave constant, okay, is gonna change depending on the boundary condition, and we're gonna also continue on how the actual amplitudes are related to each other. Okay, so I'm almost running out of the battery. I'm gonna stop this video here and I'm gonna start video number 2 doing the rest of it.